Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗙𝗢𝗟𝗟𝗢 and today we're playing Guessing Game 1 from PicoCTF, another Binary Exploitation challenge, and this one is actually medium difficulty, nothing than the rest we have done so far. So let's go, we download the files, don't forget 𝗪𝗪𝗧𝗪𝗪𝗪 as always, and we see that first of all the challenge is a 64-bit LSB executable, statically linked. That means we cannot perform attacks like ret2syscall. libc is out of the view. Let's review the source code right now. We see that we have a buff size of 100, an increment function that adds 1 to whatever it takes, a getRandom function that returns rand percentage buff size, which is kinda sus because rand here does not take any specific seed. It has the same all the time. So the random it will return, it's a pseudorandom, not an actual random number. Then we have the do stuff function that calls getRandom, which returns a pseudorandom, and after that it increments its value by 1. Here it takes if we have guessed the correct number, pseudorandom number, and if so it returns res, and here it calls win, which has a massive buffer overflow because buff size was 100 and f gets reads up to 360. So that's what we're gonna do. We're gonna find the pseudorandom number and after that exploit this huge buffer overflow to do a technique called ret2syscall, which actually we craft syscalls for 𝗪𝗪𝗟𝗪𝗪𝗪 in order to spawn cell for us. And here I have made a theory template. First of all, our prologue, import the library, fname_val, the remote instance, analyze the binary with 𝗪𝗘, and find some rope gadgets inside. And let's see what we've got. First of all, we have to know that BSS is a writable segment in memory, and our approach here is do two syscalls. The first one is call read stdin keyboard into BSS and up to 0x100 bytes. So in order to do that, we have to set rax to 0, RDI to 0, RSI to the address in BSS, and after that RDX to 0x100. If you don't believe me, there is a site that tells you exactly what you need to do. So for example, here is sysexecv needs 59 into rax, and then it tells you the rest of the registers. If we go up, the first one we see is read, rax should be 0, and then the rest we know them, RDI, RSI, RDX. And for the second syscall, we actually need to call execv_binsh, and rax shall have 59 RDI, the address of binsh, which we will read inside the BSS segment of the binary, RSI and RDX 0. This is the dynamic way to do it. We can find the gadgets like this. So I have found all of them. Spoiler, the syscall did not work in the read as I wanted it to work. So I will use a gadget like this that sets up rax to 0 and then calls syscall, and the manual way to do it is like this. We go inside the GDB, rope -- grep, and then here we have pop RDI, and we see a couple of gadgets. This is what it will return to us. The same way we're gonna find the rest, but for only the syscall one, instead of taking this gadget right here, we're gonna use this just for the read because it will zero out rax as we wanted to, and then do syscall, 2 commands in one, 2 gadgets in one. I will place it here. We also need to find the lucky number, pseudorandom number. Again, inside GDB, we set a breakpoint to do stuff. We run, and we actually need to get here that calls getRandom and see what it will return. Next instruction, next. I think we're here. Alright, so it returns something that is inside rax. So let's inspect rax. We have prax. Okay, and we see that we have found our lucky pseudorandom number, which is 83. But don't be mistaken, this is not actually the number, because after that it calls the increment function, so it will add 1 to this. So our lucky number is 84. Back to the solver. Here we replace that with 84, and now it's time to start crafting our payload. We also need to find the overflow offset. Let's go again now that we have found our lucky number, cyclic 200, copy that, and then we run. 84 is the lucky number, and after that the overflow inside win function, we take this that it's on the top of the stack, cyclic -so, and we find the offset at 120. So we also replace that, and now it's time we start crafting our ret2syscall. First of all, we're gonna have pop RDI, and then p64 we want it to be 0. After that we're gonna have our pop RSI gadget here, and that needs to have the address of BSS, so we're gonna do ebss, and I like adding an offset here just to be sure that I don't overwrite something critical. Then we have pop RDX, and that shall be 0x100. And last and most important, here we need the 𝗪𝗟𝗟𝗟𝗪. This will set rax to 0 and then do the syscall. So we are done with read, and after that we are gonna do the same for our exec_ve. Pop RDI, this needs the address of ebss here, and pop RSI shall be 0, pop RDX shall be 0, and now here we want rax to have the value 59, and then we do the syscall like this. So after that we trigger the buffer. Oh, before we continue, here we're gonna add a couple of ways. I'll tell you the reason now. Because f_gets reads up to 360 bytes, so we need to fill the whole f_gets, so it will add a null byte itself at the end, and then send the string 𝗙𝗘𝗟𝗟𝗙 right into the BSS. So we're gonna do this, then send r.sendLine, and we need 𝗙𝗘𝗟𝗟𝗙 null byte, so it will go straight inside BSS. And let's run our payload, and we see that we actually managed to get the flag like this. Cat solution. Oh, cd solution ls cat solve.py, and okay, we actually see the intentional solver right here. If you want to take a look, taken from 7rocky. Nice. Okay, so that was a challenge, guys. I hope you find it useful and learned something from it. If so, leave a like and subscribe to the channel. If you have any question, leave a comment, and see you in the next one. Bye.